In this video, we're going to take a simple look at linear regression by using a bit of data that we're going to create. So first of all, what we want to come up with is something like this, where we have a set of points and we can fit a line to it. Now, a line will typically have the formula y equals mx plus b. So some coefficient times the x value plus some constant value, or could be some error. So we need to find the right y and b to plug into this formula to model our data. And we can judge that model by looking at error, or in other words, the distance between each of these points and the line that is created. That's useful for continuous variables where a number doesn't necessarily have to be a whole number, but it could be a fraction anywhere between a whole number. In other words, a continuous line, if you imagine that, as opposed to a categorical variable where we tend to have whole numbers that represent something, or whole numbers that represent words like automatic transmission or manual transmission, or gasoline, hybrid, electric, things like that would be a categorical variable. Where continuous variables saying something like percent of people who get approved for a credit card application, percent of people who voted for a certain candidate, or anything else like that where it can be a number within any kind of range. So why do we care? Well, given the data sets with features and targets, we can predict target values for features we haven't seen. So effectively, we're building a model through regression so that we can predict future data, which is the whole idea behind machine learning. Lots of examples of this. Given hours studying, we can predict GPA. Given amounts spent on advertising, we can predict market share. Given the features on a vehicle, we could predict its selling price. Given credit history or length of longest account open or days of delinquency, we can predict approval for a loan, or more specifically, predict the ability of a customer to pay back. We assume the features and target exhibit a general and consistent linear relationship. So when we're thinking y equals mx plus b, we're thinking of a line. This is where a lot of the pre-processing of data can come in. If you notice there's an exponential relationship, you can make that a bit of a better fit for a model by performing a logarithmic transformation on it. That's one example. There are several other examples where you can try to make data look a bit more linear to fit a linear model. So what we're going to do is generate some random data with our feature and target values using some of the built-in mechanisms and libraries that we have in Python. We're going to create a linear regression model, which is actually quite straightforward. We'll fit the model with our training data, and then we'll plot a regression line with the training data using matplotlib, and then we'll evaluate. After that, we're going to go back and turn a few dials and tweak a few things to see how we can impact the regression model, or specifically what impacts the score of the regression model. So let's start by jumping right in. I start by using the imports that we're going to need for this notebook. Now let's see what happens when we call numpy's random function and we pass in a shape of 20 to 1. We get a list of random numbers between 0 and 1 effectively. So let's multiply that by 30. Now you see we get a list of numbers between 0 and essentially 30. So we can save this to x. So effectively, x is a series of random numbers between 0 and 30 that are floats. They do include decimals. Now let's cut x in half. And not surprisingly, we see a list of values between 0 and probably about 15. Looks like the highest we have is 12.6. But given the randomness of this, I'm sure we could run a few more times and get a little closer to 15. Now let's add 1 to that. Okay, you see a few, now it's interesting, now run that whole unit again, and we see that we effectively have a range of 1 to 16 at this point. It reran this randomness up above since I'm still executing the same cell, but nonetheless, we see our range is about 1 to 16 here. Now let's add a bit more randomness to this lower line. I'll start just by taking the shape of our x collection and passing it to numpy's random.normal function, and then we'll print out the result of that. And we see here mostly some smaller numbers that follow a normal distribution. So let's put this all together now on this lower line. So that gives us a bit of randomness in our model. And now we finally end up with a range of numbers. It looks like lowest number is somewhere in the 1 range, highest number in the 15 range. So we're still in that roughly 1 to 15. And we know that we've added a couple things here, but x is the primary variable here. We're cutting that in half, adding 1, and then adding this normal distribution. Let's assign this to a variable called y. And just for fun, let's go ahead and print out some information here. Let's print all the values in x and all the values in y, and then confirm their shapes as well. And so we see x value here is 13 and change, y value is 6 and change, x value 19, y value 10. So sure enough, you see there's a bit of correlation between these two numbers, where the number on the right is roughly half of what's on the left. And the roughly is accounted for by the +1 and then the normal distribution, which is adding a bit of noise there. But nonetheless, you can typically see a relationship between these two. Incidentally, that relationship is a bit less noticeable as we get to lower numbers, but you see the higher numbers, you can certainly see a distinction there. Now let's add our linear regression model. This is actually fairly straightforward. So what we do here is we instantiate the linear regression object and we save it into the variable called model. And then we call model.fit and we pass in the x, which is the features, and the y, which is what we're going to predict. This builds up the model and the formula that the model is going to use. And then we print out the score of the model. The score is an r² score, which is looking at the distance between the predicted value and the actual value for each of our elements. Let's go ahead and graph our regression line, and then we'll go back and we'll play with our underlying data and see how that impacts the model score. So first of all, I'm going to use a bit of an interesting approach to draw a regression line here. np.linspace 0, 30, 100 is creating 100 evenly spaced values between 0 and 30. And it's assigning that to x new. Now, model.predict x new, what it's going to do is it's going to take those 100 items, apply the regression model to it, and then compute the y value that is drawn from that x new 100 items. This effectively gives us a straight line that represents the regression formula as soon as we put on a chart. Now we can go ahead and add a bit of plotting information. So PLT subplots, we get our figure and our axis, we go ahead and add a title, and now we're going to do a scatter plot with the original x and y values, which were those 20 values we came up at the very top. The scatter plot effectively means we're going to put dots on the chart. Now we're going to do a linear plot of this regression line that we came up with up above, and we're going to be able to compare that to the scatter plot. We'll simply add a few more labels and show the plot. So if you take a look here, the blue line is our regression line, which is those 100 x values put into our regression model to give us a continuous line of 100 predictions effectively, which gives us this straight line. And then the green dots represent our original data we started with, which was the 20 random values multiplied by 30 for x, and then take half of that, add 1 plus some normal distribution noise for y, and that's what gives us this line. Now you see it looks fairly reasonable because the line fits fairly well to all of these scattered dots that we have here, but it doesn't fit perfectly. If it fit perfectly, we would have overfit, which means we're starting to fit to error. But this line looks pretty good. You see many dots are very near the line. Some dots a little bit further away, especially as we get higher numbers because of that multiplication impact that we have in there. But nonetheless, we see that fits our line fairly well. And if we want, we can see the coefficient, or the m value that was assigned by this model, just by asking for its COEF value. We see here it predicts a y is an x times 0.472, which there again feels about right looking at the graph that we have here. Now just for fun, let's go back and add some outlier data and see how that changes our model. Up towards the top, where I initiated this model with a bit of mathematical data, I can append some new numbers. So note I'm going to use np.concatenate, which is a function that will append two collections together. I used np.concatenate because we effectively have a two-dimensional list here. So I want to say, okay, add 2 and 3 to the bottom of the X collection, and add 10 and 20 to the bottom of the Y collection. Now, if you look at the formula up above, you'll see that these numbers are outliers because the Y is usually half of X plus 1 plus some randomness. And here we're saying that Y is 5 times X in this case, and Y is almost 7 times X in this case. So they're definitely going to be outliers. Let's go ahead and take a look at what we get as a result. And you see, sure enough, we have the normal generated data, then we have our outlier data. Now here's where things are going to get interesting. Remember our model score before we had those outliers. Let's try it again. And you notice it goes way, way down. It went from about 93% accuracy to about 10% accuracy. We can redraw our chart again, and we can see that, sure enough, a couple of outliers really throw things off. And that's why it's important when you're looking at data and pre-processing data to do a bit of graphing and look for outliers that you might want to remove from your analysis. Because they can have a supersized result on the regression formula that results. Now this is a bit of a special case because we have 2 outliers in a relatively small data set. 2 outliers in a larger data set probably wouldn't have as much impact, but nonetheless. Let's take out the really big outlier, run this one more time, and let's see what our score is. Remember, the first time we ran it was around 93–94%. Then with a couple outliers, it dropped to 10%. Now with just one outlier, we see it's up to 80%. And I did get rid of the biggest outlier there. We go ahead and run the graph again, and you see, sure enough, we have our outlier here, but no longer the outlier that was way up here. And we see that our coefficient's still about the same, but nonetheless, we see that with just one outlier instead of 2, our model has become a little bit more specific. So that's a bit of a graphical or visual look at regression data and training a regression model and scoring a regression model and the impact of outliers on a regression model. Several of these subjects we'll get into a little bit deeper, including how to evaluate results of a regression analysis. So I hope you found this video helpful, and I look forward to reading your comments. Thank you.